Does it work? Yeah. Okay.
Okay, so our next speaker is Francesco Dagnino from the University of Genova, and he will talk us about relational doctrines, monads, and Lax algebras. So, Francesco, please go.
Oh, thanks, Francesco, for the introduction. So, and thank you to the program committee for having me here. So, first of all, a disclaimer. So maybe during the talk I will be inconsistent with the slides. So please pay a lot of attention, and if I get inconsistent, stop me so that we can recover consistency. And so this talk is just I don't know, a collection of sparse ideas about relational stuff, and I think it's the result of a lot of discussions with many people, Francesco, Fabio, Pino, and some others I forgot. So it's nothing stable. It's just ongoing work. So any suggestion or criticism is more than welcome. So let's start from the very beginning. So in usually logic, in predicate logic, the basic notion is that of a predicate or a proposition of some sort, and basically unary predicates. So you represent, from a semantic perspective, they can be thought of as subset of a given set. And you can talk about relations if you allow yourself to have more than one variable, and then you take a formula over this context with many variables, and this is a relation. And you can define relational constructs in terms of first-order connectives, basically. So the composition, you can define the relation, the composition of binary relation as by an existential quantification and a conjunction. This is standard stuff. But there is another approach to logic, which is, let's say, relational calculus or relational logic, where instead the primitive concepts are binary relations themselves, and where all relational constructs are taken as primitive logical operations instead of being derived from the first-order connectives. And the main one are, let's say, relational composition, identity, the converse, and then usually some Boolean operations, which are the standard ones. And this has some advantages because you get a complete variable-free language where you do not need really individual variables in this setting. And that's nice because it is more suited when you have to move from the standard logic to more quantitative or substructural setting, where having compound contexts with many variables is something which is quite difficult to handle. And moreover, it is less expressive than usual first-order logic, but is still quite expressive. And as we will see, I hope, it allows us to do many things. So from a categorical point of view, to do relational stuff, the usual setups are, let's say, allegories or Cartesian by categories are two different things, of course, but roughly these are categories enriched over posets with some additional structure. They are quite natural and works very well, but let's say they have a lot logical principles which are implicit and which are there under the hood, especially some choice rules, which maybe one do not like, especially if you want to be constructive. So in usual predicate logics, to avoid this and really separate the logic and the algebraic part, one moves to a fibered setting, and doctrines are a very simple fibered setting, which nevertheless are quite expressive and useful. So the goal of this talk is hopefully to show you how doctrines can be used to do relational reasoning, or let's say to do relational logic, and see some applications to, let's say, Lax algebras. This is the outline of the talk. So I will first introduce relational doctrines. Then I will show you several examples and some basic properties. And finally, I will discuss monads and the construction of the Lax algebras on these kind of doctrines. sorry, maybe I am inconsistent in the moment at this time. So that's the definition of doctrines, right?
Yes.
Yeah. So sorry. So doctrines are just contravariant functors, as you can see, from a category to the category of posets. And the intuition is that the base category models, as I said, the algebraic part, so objects we are interested in and transformations between them. And every fiber, so every poset above every object in the base category can be thought of as the poset of predicate on that object ordered by logical entailments. And the action on morphisms of the base category is instead substitution. And one usually requires the base category to have finite products in order to allow for many variables. So as I was saying, this is the goal, right? Yes. And this is the outline, exactly. Right? So I have already discussed this. So have you any questions so far before I move on? Okay. Relational doctrines. So to define relational doctrines, I would need a base category, so the object and the transformation I want, and a relation between such objects and their basic structure. And in this talk, I will just focus on relational composition and identities for simplicity. So what is a relational doctrine? So we have a base category to model our objects, and a contravariant functor from the product of the category with itself to the category of posets. And this models for each pair of objects the poset of relations ordered by some kind of logical entailment. And the action on pairs of morphisms represent reindexing, so substitution in a sense. Okay. Then I have to define identities. And relational identities are just a family of objects in the fiber over A and A. So an identity relation is a relation from A to itself. And we require this family to be to satisfy this lax naturality condition, let's say. Basically, we require each arrow in the base category to preserve identity relations. That's pretty standard. So basically, this says that an arrow maps equal elements to equal elements, roughly. Okay. Then we have relational composition, and that's, again, pretty simple. So we require, we take three objects, and we require a family of monotone maps from relation from A to B times relation from B to C to relation from A to C. And so which is monotone, so preserve the order. And moreover, we require, again, this lax naturality condition. So this says that if we first reindex along F and G, the first relation, and then we reindex along G and H, the second relation, and then we compose, we get something which is smaller than doing first the relational composition and then reindex along F and H. So notice that here the middle arrow disappears. And moreover, we require the usual equational axioms for relational composition and identity. So relational composition is associative, and the identity relation is the neutral element. Okay, fair enough. These are relational doctrines, pretty simple. But let's have a more structured perspective on this. So to do so, I need to introduce morphisms between doctrines. So a morphism between two doctrines P and Q is just a pair of a functor between the base categories of the two doctrines and a natural transformation which lifts a predicate over an object in the first category to a predicate or in the second doctrine over the action of the functor on that object. So it goes from P of X to Q of F of X, basically. And we require this to be lax natural. This is something for those of you who are used to work with doctrines, which is a bit unusual because usually this is the second component is a strict natural transformation, but here we really need lax naturality, and I think we will see at some point the reason why. But basically, yeah, maybe it's in the next slide. And so this is the morphisms of doctrines, and given that, we can describe the structure of a relational doctrines as algebraic structure inside the category of doctrines, basically. So what is the identity? It's just a morphism from the doctrine, the trivial doctrine, basically, which maps every object in C to the singleton poset, to the doctrine, to our doctrine of relations, which has as a functor between base categories the diagonal functor, which says that we want the identity relation to be a relation with the same domain and codomain. And the fact that the domain is the trivial doctrine means that we pick one element in all these fibers, basically. And the lax naturality models the fact that we only want arrows to preserve identity relations and not to, let's say, reflex. If this transformation is strictly natural, this basically means that every arrow in the base category is injective because we have also the other direction. So if f of x is equal to f of y, then x is equal to y, which is not which is a bit strange, I think. So that's the point for the identity. And for composition, we have to consider this pullbacks with pullback. So we have basically projections from our doctrine of relations to the trivial doctrine, which projects on the first, on the second component, on the base categories, and which trivializes the relations. So it's the terminal arrow, basically. And we do this pullback, and so the result, which is R2, is a doctrine which has as base category the product of 3 copies of C, and the fiber over A, B, and C is the product of relations from A to B and relations from B to C, basically. And then relational composition is just an arrow from this pullback to the doctrine of relation, which has the first and the third projection as base functor. And with our equational axioms, what we get basically is that this stuff gives us an internal category to the category of doctrines. So this is some kind of more structured definition of what relational doctrine is. Questions so far? Okay. So let's see some examples. So the first one are quantile valued relations. So the base category is set. We fix a quantile, which is a complete lattice with a monoidal operation which distributes over arbitrary joints. And relations are just functions. Relations from A to B are functions from the product of A and B to the underlying set of the quantile with the pointwise order. And reindexing is given by precomposition. So here the identity relation is the function which maps to the unit of the quantile if the two elements are equal, and to the bottom element if the two elements are different. And the relational composition is given by taking this sup, this join, basically, of the monoidal product of the two relations. So these examples cover many usual examples in relational reasoning. So here we have standard relation, metric relations, modal relations, and many others. And actually, this stuff can be generalized to an arbitrary elementary existential primary linear doctrine, elementary and existential linear doctrine, which is a doctrine modeling a fragment of linear logic enriched with the existential quantification and usual equality. Okay, so here we have another examples, which are matrices. So if we take an ordered semi-ring and we can define we can consider the category of finite sets with all their functions. And the doctrine is similar to the previous one. So maps, so relations from A to B are maps from the product to the underlying set of the semiring with the pointwise order and precomposition as reindexing. So here the identity is the Kronecker delta, basically, and relational composition is given by matrix multiplication, basically. Notice that that sum is finite because we are working with finite sets. And we can extend all this stuff also to arbitrary sets in a couple of ways. Maybe we can discuss it afterwards if you're interested. Okay, so another example are spans inside the category with weak pullbacks. And so here the order between spans is the usual one. So we say that a span is smaller than another if there exists an arrow which makes the two triangle, an arrow between the vertices which makes the two triangle commute. And precomposition is given by, reindexing is given by weak pullbacks. The identity is the identity span, and the relational composition is the usual composition of span. Oh, sorry, there is, of course, a poset reflection there in the definition of the fibers because we have just weak pullbacks, and so we need to, so that is just a full partial order. Finally, if we take a category enriched over posets, we can define in the standard way the category of maps in this C, where the objects are the same and the arrows are basically adjunctions inside the category C in the direction of the left adjoints. This basically models, let's say, functional relations inside that post-enriched function, post-enriched category. And then we can define a relational doctrine where the base category is the category of maps, and the fibers, the relation are all the arrows in the category C. And so relational composition is the composition of C, and reindexing is given by that weird composition. So we first precompose with the left adjoint, and we post-compose with the right adjoint, a relation R, which is an arrow. Okay. Now, what can we do with a relational doctrine? This is just useful for the next slide. So we can define graphs of arrows in the base category. So we can represent basically arrows as spatial relations. And the definition is that one. So we just apply the reindexing along the arrow and the identity to the identity relation. And this gives us a relation from A to B, given an arrow F from A to B. And what we can also do is to get a converse of this relation, which is just obtained by reindexing in the other, swapping the two arrows, basically. And the nice thing is that these two inequalities holds, which basically says that the graph of an arrow in the base category is a functional and total relation in the relational doctrine. So it's really a function. And last, using graphs, we can encode reindexing by means of relational composition in that way. So we precompose with F and we postcompose with the converse of G for reindexing. But we also discover that we have all left adjoints to this reindexing, just doing the relational composition in the other direction. And this basically means that we not only have reindexing, but we also have images along all arrows in the base category. Okay. Monads. So the last part is about lax algebras and monads on relational doctrines. So to define monads on relational doctrines, I first need to define a suitable two category of this stuff. That's, again, pretty standard. So the objects are relational doctrines. One arrows are consist of a functor between the base category and a lax natural transformation between the doctrines of relations. And notice that these basically are usual relators or lax extension of functors for those of you who are used to relational stuff. And two arrows are just the natural transformations between the underlying functors of the one arrow, which has to satisfy that usual inequality that basically says that these natural transformations respect the second component of the one arrow. Of course, this is important. We require the second component of one arrows to preserve relational composition and identities in a strict way. This is not very usual for relational liftings because they require to preserve composition and identities in a lax way. But in this setting, it's better to work in this way because otherwise there are some compositions which fail in the category of monads. Okay, so this is the two category, and we can consider monads inside these two category. And this is the definition spelled out, basically, and is the same thing of a relational extension of a monad, again, for those of you who are used with relational stuff. And for those of you who are used to category theory, it's just a monad inside the two category of doctrines, so nothing interesting. But let me remark this, because the construction of spans I showed you, which is, again, pretty standard, nothing very new, extends to a two-functor from the category of categories from the two category of categories with weak pullbacks and weak pullbacks preserving functors to the two category of relational doctrines. And so these two functors maps monads to monads, and basically these realize the well-known bar extensions of monads in an abstract setting, basically. Okay, lax algebras, and then I conclude. How much time do I have?
5 minutes.
Okay, I hope I will finish. So we take a relational doctrine and a monad on it, and we want to construct a category of lax algebras. So basically, this follows what people working on monoidal topology do. They work basically on a category of sets. Here we work on an arbitrary relational doctrine. So given this monad, we define this category of lax algebras where objects are pairs of an object in the base category and a relation from T of X to X, right? Or T of A to A, I don't remember. From T of A to A, and which has to satisfy a couple of inequalities, which are, if you look at it, look at them, they are the usual axiom for an algebra for a monad, but expressed in a lax way, so with an inequality instead of an equality. And this is possible because we are working with relations and not just with arrows. And morphisms are just arrows between the carriers of the algebras, which has to preserve the algebra, which is given by the relation. So again, this is the same thing as a homomorphism between usual algebras, but here again it is not strict but lax, because we only want relations to be preserved and not to be reflected in a sense. And okay, and then we can define a doctrine on this in a pretty simple way. So we take relations between two algebras to be all the relations between their underlying objects. And that's it. So the rest of the structure is the same of the original doctrine. And as people working on monoidal topology showed, these constructions covers many examples, which are pretty usual in mathematics, like preordered set, Lauvier metric spaces, topological spaces, and all this stuff are instances of this construction. And what we can prove is that this construction has a similar property to the Eilenberg-Moore construction, which is given by this equivalence, this isomorphism between home categories, where the home category on the left is the home category in the category of in the two category of relational doctrines, while on the right we have the home category of the two category of monads. But this is not the usual two category of monads, because we have to fill, there is a difference in monads morphism, because our notion of algebras are not arrows in the base category, but is a relational notion of algebra. And so we need to fill the squares of monads morphisms by a family of relations and not by a natural transformation, which has to satisfy a bunch of axioms. I have not time to go into the details, but are what you expect, I think, and what is needed to make the isomorphism work, basically. So that's it. There is a lot of things which are open, so probably this is just a first step towards working with doctrines and relational stuff. What I would like to do in the future is to really use these things to reason about more sophisticated things like choice rules or quotients and this kind of stuff in a purely relational way. So without using products or existential quantification, but just using relational stuff. So thank you for the attention.
All right, so thank you, Francesco. Questions?
Thanks a lot for the very nice talk. I missed one point, but when you do the construction of maps, this allow you to move from a relational doctrine to a traditional doctrine, or
No, I do the construction of maps because I need a base category to identify, let's say, the algebraic part, and I need to define the reindexing along arrows in the base category. And if you remember the definition, to define that reindexing, I need the right adjoint. So I cannot take the full Poisson-Rich category as base category of the relational doctrine, because in that setting, not all arrows are adjoints. And so I could not define the reindexing part. Basically, I split the logic of relations and the algebraic part, where we have objects and transformations between them, which are functional relations, basically. I don't know if I answered.
This was clear to me. Okay, but maybe you can always reduce a relational doctrine to an existential one, because somehow.
No, because I do not have products in the base category. So to get an existential doctrine, I need to have products, because, as I said at the beginning, I need to. So basically, working with existential doctrines is like talking about relations in a predicate logic. And so to do this, I need to have many variables. And to have many variables, I need products in the base category.
Okay.
And that's what I would like to avoid, because, for instance, working in a quantitative setting, what you usually get in the base category is just a monoidal product and not a Cartesian product, and so having existential quantifiers becomes difficult.
Okay, but so as soon as you have a Cartesian product, you end up into the relational doctrine may collapse with the.
That's a point for future work. I need to. I think I also need some kind of binary connective on the fibers. Okay. At least a tensor, so a linear conjunction, to get back an existential doctrine.
Thanks a lot.
Also, just a few comments, if I have time, one more comment. On this, I'm aware of a paper which relates Cartesian bicategories and existential elementary doctrines. And the point there is to get the equivalence, you need existential doctrines with a rule of choice. While if you work with relational doctrines, probably, because I have to check these details we were discussing, you get an equivalence with existential doctrines not necessarily having the rule of unique choice, as in Cartesian bicategories.
I have a question, maybe perhaps related to Filippo's. So if you forget about the hypothesis of the base category having products, do you expect relational doctrines to have some kind of universal property among doctrines? Or I mean, can you imagine some monad or something such that they are coalgebras for a monad or something like that?
So they are categories, they are internal categories. So I'm not really, I'm a computer scientist, I'm not really expert on all these details, but maybe that internal categories are algebras or not. At least I think they are models for a sketch.
Yes, I think so too.
And so we characterize in that way, I think.
All right, thanks.
Okay, I think we are done and almost in time. So let us thank again Francesco. And now we have the coffee break, so we will meet again here in a few minutes, actually.
Mi ricordo, c'è coffee break?